Hello and welcome to the Optical Society webinar, Electronic Photonic Integrated Circuits Research Training. I'll now turn it over to Hannah Walter.
Thank you, Natalie. Hello, my name is Hannah Walter, and I am the Technical Community Manager here at the Optical Society. I'm pleased to welcome you to today's webinar. This webinar is presented by the OSA NAIL Photonics Technical Group, one of 42 different technical groups offered by OSA to bring together the communities around selected subfields of optics and photonics. It is through the efforts of the OSA members who volunteer to lead these groups that we are able to offer unique and engaging events tailored to your interests, such as today's webinar presentation. Now, it is my pleasure to welcome Volker Sorger, the chair of the NAIL Photonics Technical Group, who will tell you a bit more about this group and introduce today's presentation. Volker?
Thank you so much, Hannah. My name is Volker Sorger, and I'm the chair of the Nanophotonics Technical Group for OSA. So we are a team of 6, as you can see here on the current slide, and we are organizing events around nanophotonics with the objective to bring a community together, stir research discussions, and promote the field in general. And so things we do in general, for instance, is poster sessions. We had a poster session at Clio recently. We also had an incubator meeting, a topical meeting at the OSA headquarters relating to promoting the field as well. We called it actually last year nanophotonic devices beyond classical limits. And we also organize these webinars and, again, these special events that we talked about before. And I believe with this, yes, how to find us, essentially this can be seen here. So we have a web presence at the OSA webpage. It's basically you see here on the lower left. And we, of course, also at various various social media, for instance, here, at Twitter and Facebook and so on. If you're interested in joining our community and joining the discussions, please email us, reach out to us anytime. And in particular, we often have needs for bloggers as well, and there might be small incentives to do so as issued from OSA. So with this, it's my great pleasure to introduce our today's speaker. Is Professor Dr. Lukas Kwiatkowski. He's an associate professor of electrical and computer engineering at the University of British Columbia in Vancouver, Canada. He earned his bachelor's in engineering in electrical engineering from McGill University in 1998 and a PhD from the University of California in Berkeley in 2004. Well, I definitely have good memories to California too. Dr. Kwiatkowski recently received the Killian Teaching Award at the University of British Columbia in 2014. He also co-authored the book Silicon Photonics Design. He's also the program director for the NSERC CREATE Silicon Electronic Photonic Integrated Circuits training program in Canada and has been teaching silicon photonic workshop and courses since 2007. So he's really an expert in this field, and we're very excited to have him with us today. And with this further ado, I'd like to turn it over to Lukas. Please go ahead.
Great. Thank you, Volker. Thank you for the introduction, and thank you to the OSA for hosting me and inviting me to join this webinar. So in the audience, I recognize some people, and I also see a lot of new faces, new names. So thank you very much for joining me today. So I'll be talking about what we call the SiEPIC program in Canada. So NSERC is the funding agency similar to the NIH or NSF in the United States, and the topic is silicon photonics. And so the motivation for silicon photonics, I think most people have the concept is that we have billions and billions of dollars invested in CMOS electronics, and we'd like to take advantage of this for optics, for integrated optics. And so in particular, what we want to take advantage of is the mature materials processing and the design tools that are already available. And libraries, of course, we need to develop libraries for optical components. So in terms of silicon photonics, we can talk about integrated optics and we can talk about integrated electronics. And so the name SiEPIC, where it came from, is Silicon Electronic and Photonic Integrated Circuits. And how this relates to our program is that most of the research that's going on in Canada in silicon photonics is using the fabless approach. So we take advantage of all the foundries that are generously providing their fabrication, and most of the students involved are and postdocs and companies are using the fabless model to make progress. So in the webinar today, I'm going to speak about primarily about the SiEPIC program, and so there's going to be a focus on workshops that we do, and so most of the research really comes out of the workshops, and people continue on for a year afterwards the workshops, and then do design, and then we have a community of people who are engaged in this area. Then I'm also going to talk about some other sort of shorter opportunities. These workshops are typically sort of 5 to 7 days long. We also started doing short courses at conferences, and then we're launching an online course which also has fabrication, so I'll describe that. And then towards the end, I'll describe some of the research outcomes from the program. I think there's way too many to go through all of them, and so I may have to kind of cut that part short. I should say that I posted these slides on LinkedIn, and so if you want to find the slides, they're available for download as a PDF, and so you can go ahead and download. Okay, so let's jump into the CREATE program. So starting with history, we started actually made a mistake. It was actually 2008 was the first workshop we offered. So we started offering these workshops in 2008, and they became quite successful. People really enjoyed them. One of the things that I found very surprising was that it was actually possible to publish in the field of silicon photonics after students were able to take a single workshop. And so even though people were doing things like waveguides and so on, there was still a lot of work to be done in the field. And so that was very encouraging. And so then a few years later in 2012, we got a grant from the Canadian government. And this is a 6-year program to essentially expand these workshops. And so originally we started only doing passive optics, and then gradually we started doing active silicon photonics for modulators and so on, CMOS electronics, and then now we're launching another workshop on system integration, which I'll describe today as well. So the original grant was 5 universities: University of British Columbia, McGill, McMaster, Sherbrooke, and Ottawa. And we also have instructors and participations and collaborations from Laval University and University of Toronto, as well as companies both in Canada and outside who come in and help teach and so on. And we have a webpage, siepic.ubc.ca. So let's discuss the program objectives. So the objective is to train people to be the designers, and I highlight innovative designers. And the idea is to be able to go through the entire design fabricate cycle. And so the students and participants focus on design. We get the foundries to fabricate things, and then we do the testing at all the various universities. And the workshops are what really kind of glues our community together, where we get together once a year, and then people take these workshops and then go home and do the research. And so, of course, these research is supporting their thesis research or their startup companies and so on. For the students involved, we also encourage industrial interaction, and so we have internship opportunities, as well as professional development training. Here I provide a list of the professors who were involved in the original grant application. I mentioned this has grown a little bit since then with additional instructors. So from UBC, we have myself and Professor Yeager and Professor Jeff Young, so you'll see some research results from that. From McGill, we have Professor Odile Leboiron-Ladouceur and Dave Plant. Again, you'll see some work from there, mainly on communications. McMaster, you'll see results from Professor Andy Knight's group. We have Ottawa University and Sherbrooke as well. And collaborators, so Professor Joyce Poon, you'll see some of her nice work on polarization optics towards the end. We have Sophie Larochelle and Wei Shi from Laval University. And agencies that support this work, so these are essentially non-profit type organizations. CMC Microsystems, this is the equivalent of MOSIS in the United States, and I'll discuss that in a second. And we also have C2MI and the National Research Council, plus several companies who are providing internships. So CMC is an organization, a nonprofit, that provides industrial fabrication. So these are the foundries around the world, and provides those primarily to the universities, but also to companies in Canada. CMC has about 50 member universities. There's 1,000 professors involved, and there's about 700 companies who have used CMC services. Now, what's been really impressive is how much silicon photonics CMC has been doing. There's been, in the last 4 years, about 300 designs that have been fabricated through silicon photonic foundries, through CMC. And so CMC actually provides all these services to our research program in Canada. by organizing these multi-project wafer fabrication runs, and they also provide some subsidies for students to travel and for the chip fabrication. They also provide all the design software, so all our workshops come with Mentor graphics and so on, software and Cadence, and so this is provided by CMC. And of course, their staff have make lots of intellectual and academic contributions to the development of workshops, the design kits, and teaching and so on. So this is a very good relationship we have, and we're very lucky in Canada to have this organization that's heavily invested in Canadian research and silicon photonics in particular. So let's talk about the core of the program, which is the workshops. And so I mentioned we have now 4 workshops. The first one, which will be coming around 1 year from now, roughly, is the passive photonics workshop. And so this is, essentially kind of what's been happening in silicon photonics in the last 10 or 15 years, which is things like ring resonators and grating couplers to get the light in and out. Participants in this can make a variety of optical filters and splitters, and the fabrication is done through either IMEC or IME in Singapore. The next workshop, so now I think we're on our 4th version of this one, is coming up in August, and this is active silicon photonics. So this takes everything that people have done in the passive workshop and adds dopants and germanium so that you can have to make modulators and detectors. And again, the fabrication is through CMC IME, and this is a customized IME run that's run out of CMC Microsystems. In September, we're going to have another workshop on electronics, and this is electronics specifically for photonics. And so we talk about how to design drivers for ring resonators and traveling wave modulators, how to design TIA amplifiers for the detectors, and we also talk about optical link analysis. And this workshop includes fabrication through IBM, and I believe this is the 0.13 micron technology that we're using. And the final workshop, this one we're very excited about. We're completely redoing it this year. This is our 2nd time we're doing it. It's called the Systems Integration and Packaging, and I'll describe what this means. But it's essentially just trying to push the envelope in terms of where the field is at, in terms of promoting people to make, especially at the universities, we focus a lot on components. And so this is pushing the university community to get more involved in integration and trying to make systems, which of course companies are very interested in doing. So these workshops are open to everybody. We have people from industry, we have people from academics. Over 20 universities have come so far. So I'll give you some numbers. Since 2008, we've had 14 workshops in total. We've had 273 participants coming from about 41 different institutions, of which 26 are universities, and 23 people from companies, 53 different professors being the supervisors of the students. We've had some professors attend as well. And the most active universities are McGill, UBC, Laval, McMaster, and Toronto. So here's a chart that shows the participation, just so you can see kind of the scale of this operation. It's relatively small. Part of this challenge is that everybody has to fly in to one city, and we rotate the workshops, let's say Vancouver, Montreal, and so on. And so this requires people to essentially as if you're going for a conference, but it's 9 to 5 all day for 5 days. A very intense and fun experience. But we have numbers that are typically in the 20 to 30 range. And the passives workshop is the one that's been going on since 2008. And I'm actually still surprised that we haven't saturated the market. In fact, actually, we see slight growth in the passive silicon photonics. And so this is really our introductory workshop. The next point is who fabricates these chips for us. And so I mentioned IMEC through EPIC's fab in Europe. That's been one of our main partners since 2008. We've also partnered with IME in Singapore, in particular for the modulators and detectors. And as well, they have a nice module for doing edge coupling. There's other foundries, of course, I should mention around the world. We have IHP, LEDI, VTT, and so on. So there's plenty of fabrication opportunities, which is really a nice time for the silicon photonics field. One of the challenges we find with the foundries is that they typically take maybe 3 to 6 to 9 months to turn around the chips. And so a lot of the students really like to have more rapid feedback. And so we've been working with electron beam lithography at the University of Washington. And so we've probably done about 20 runs. We do them every 2 months. And this allows us to get results back within a week, maybe within 2 weeks, including all the measurements. And I'll talk a little bit about that a little bit more in a minute. So let's discuss the active silicon photonics workshop. So this is actually chosen to be right before the IEEE Group 4 Photonics Conference. So this is the Silicon Photonics Conference, which is going to be held in Vancouver. And so we're holding it essentially right before. So the idea is that people can learn how to design silicon photonics and then come to the conference to learn about what is the state of the art in the field, and then go home and then come up with innovative designs. And we're targeting the IME silicon on insulator technology, as I described, with a few additional fabrication steps that were added, and again run through CMC. And we provide all the design tools for the whole design cycle. So typically we give people maybe 3 to 4 months to do the design. It goes off for fabrication. Eventually things come back, and then people do their test and write publications and theses and so on. The topics, of course, you'd expect ring modulators, Mach-Zehnder modulators, germanium detectors, and some thermo-optics. And the registration page and the description of this workshop are available online through the links provided. So here's typically what the design cycle looks like. And this is very similar to what the CMOS industry does. So if you look at the electronics industry, their design cycles are typically a year, maybe 2 years. And so our design cycles are roughly a year through these workshops, and so that's why we offer the workshops once a year. And so we start with a workshop that people go home, do some design modeling, write some proposals, design documents. We give people feedback all the way through this process. And then they go into the mask layout, and then we also give people feedback on their draft layouts and do all the DRC and error checking and so on. And then finally, this goes off for fabrication and then testing. Most of the universities and research labs and companies have their own infrastructure, and so they do testing. We can also host students and promote exchanges and so on. And so that's available for people. So this workshop is a new one, and I'll be posting a bit more description on LinkedIn as well, probably in the next few days if anybody's interested. But this has been something we've been kind of dreaming about for quite a few years as to what is the next, where is silicon photonics going, and the thinking is that we need to build complex systems. And if you look at some of the companies that we work with, they're using on the order of thousands, 10,000s of components. And so how do you model this? How do you assemble these systems? How do you do the electronics and the photonics together? And of course, how do you do the packaging? Packaging has kind of always been seen as the technology will die if the packaging isn't solved. And so we wanted to have a workshop that focuses on getting things right to the end, where you have something in a box. And so the way we decided to frame it this year is to actually give people very challenging problems to solve. And the idea is that for the next 12 months, people will go and tackle these and sink their teeth into the problems. And so, for example, optical interconnects, we say, okay, well, how can you design a 10 terabits per second transceiver? And so, the idea is to go an order of magnitude or 2 orders of magnitude more than what is currently available. And we know that it is possible to do it. Maybe there's some challenges, of course, and this is what we'd like teams to start thinking about doing. Similarly, for sensors, for biomedical applications and microwave photonics. We also want to ask the question of optoelectronic circuits. And so the question is, what can you do better if you combine electronics and photonics than if you only did photonics by itself or only electronics? And so, for example, maybe in cell phones, there's going to be an opportunity, or for microwave applications. And then the final topic we're going to have is nano-optomechanics. And so through the IME process, we included actually an etch that gives you access to the waveguides. And so this is useful for both the sensors and the nano optics. For nano-optics, you can also etch these devices and release them and have suspended waveguides. So this workshop is going to be held at McGill University in Montreal, and it's going to be November 2nd to 6th. So the registration page is not yet available, but like I said, I'll be posting something on LinkedIn and links and so on. We've also started reaching out to the broader community. I think the SiEPIC program really hasn't done any advertising in the earlier years. We were focused on the Canadian markets and so on. So we actually started going out a little bit abroad, and so we went to San Diego to the IEEE Photonics conference last year, and we had 89 people. And this was a short course; it was 3 hours. But what was neat was we included a fabrication run as part of this workshop. And so 4 weeks after the conference, we actually gave people experimental results back, and so this was included the fabrication and the testing. And we're encouraged by this, by interest in the community. We're going to do this again. So we're going to do this at the Group 4 Photonics conference in Vancouver. So that's going to be another 3-hour short course. This is going to be a kind of a schematic-driven PDK-based flow, and so this is going to be running on the Mentor Graphics numerical tools. And at the IEEE Photonics conference again, we're going to have a focus session on sub-wavelength grading materials and metamaterials. So that'll be how to model, how to design these kind of quite interesting structures. And then the final short course is this online course, and that's starting in about 2 weeks or so, July 7th. And it's a 6-week-long program, and again, it has the fabrication and testing included in it. So how do we do this fabrication and testing? Let me describe the rapid prototyping that we have access to. So this is at the University of Washington. It's a mature process using a very expensive sort of $5 million scale electron beam lithography machine. Our costs are on the order of about $1,000 per chip, maybe a little bit more, for the most basic process, which is a single etch process. But we've done more complicated things, and so if people are interested in mimicking an IME or IMEC process, we can do multiple etches, and we put heaters on chips and so on. And so using this, because we're doing these things every 2 months, and we have an automated probe station, it really makes it quite easy for us to offer these workshops that take advantage of the fabrication and the testing. And so here's a picture of one of the test setups that we have. This setup is actually available through CMC Microsystems. You can see the faint link there where it says Lab Tour. If you take this lab tour, there's a video which shows you how the setup works, and there's links on the YouTube page that take you to where you can get this set up. This is distributed now from CMC Microsystems. We've shipped about 10 of these to universities and companies, and they're not terribly expensive. I actually don't know what the real cost or the for sale cost is, but the parts are on the order of 10 or 20K plus the laser. And we have software that's been written, I guess, as open source in MATLAB and Python. So to make these work in the single etch process, in contrast to what's available from the foundries. So in the foundries, you may be familiar with the grading couplers are shallow etched. Here we want to minimize our costs and make it as rapid as possible. And so what we've done is we've done a single etch grading coupler. So this is very similar to the work from the National Research Council, using these sort of metamaterial sub-wavelength type structures. And again, these are focusing. And the performance of these is similar to what you would get with a shallow etch. And so we provide these in library, both TE and TM polarization. And we have these PDKs, both available as sort of a GDS style PDK where you do things in whatever program you want, or we have a schematic-driven PDK in Mentor Graphics. So if you're interested in accessing this fabrication, the motivation here really for me is that I want somebody else to do all the hard work, and I can sit at home and do design. And to make this really possible, it requires a community of people so we can do cost sharing. And so we have about 100 users who are kind of active on these fabrication runs. And I mentioned we do this every 2 months. And so we do these short courses through these where we give people a small design area. Now this design area is quite small. If you work out the math, this allows us to do about 1,000 people per chip, and we haven't scaled up to 1,000 people yet. So in principle, all these courses, the edX course and the conference courses, we can give people 10 times as much area and not run into any problems. So if you need more space, let me know. And the idea here is that the reason these costs are almost negligible if you have 100 people in this is because we only have one chip that's manufactured, and we don't send anything to anybody. We only do automated measurements once. Now, if you want your own chip, we can obviously fabricate multiple chips through the process, and so then the chip is roughly 1 centimeter by 1 centimeter, and you have a choice of cladding, whether it's air or oxide, and the chip is sent by FedEx to you, and the cost for academics is on the order of $1,200, and we typically take the bill and cut it by N at the end of the day. With these workshops hands-on, I mentioned the challenge of people flying around the world. And we thought, hey, can we scale this up to 10, 100, 1,000, 10,000 people? The fabrication, especially if you give people a very small amount of space, it pretty well scales to 1,000 and 10,000 people. And so we came up with an online course, and it's hosted by edX. And this includes lectures, tutorials, videos, and so on, and actually quite really nice activities online. And so there's actually a MATLAB integrated environment within the web browser, so you can actually do waveguide modeling right in the browser. You can also download all the numerical software to run simulations on your laptop. And Mentor Graphics is providing a cloud access, so you can do the design through the cloud using advanced Mentor Graphics tools. So we provide people a very short design cycle. It's actually only 2.5 weeks roughly, and then chips get fabricated, and then we measure all these devices. Now the philosophy I think is quite interesting, and the idea is that in this workshop, we don't want to drag people through this year-long process. We want to introduce people as quick as possible to silicon photonics so that they can get this sort of initial exposure, and then they can decide, well, is this a field they're interested in continuing further, or what topics are of interest. And it's kind of like seeing the forest through the trees expression, where you really want to get a big picture first of what you're going to do, and then you dive into it a little bit more detail. And so if you look at the schedule, it's week 1 is design, week 2 is mask layout, week 3 we actually have a design review. So this is a peer-based design review where the instructors and other participants provide feedback. And then we have a final deadline 20 days after the start of the course. Then it goes off for fabrication, comes back in week 5 for testing, and then finally students get to analyze the results in the last 6 weeks. And I've already talked about some of the software that's provided. So we talk about component modeling using MATLAB in numerical mode. We talk about circuit modeling using numerical interconnect in MATLAB. And we talk about layout with either a free tool called KLayout or Pixis from Mentor Graphics. And then finally data analysis with either MATLAB or Python. And so there's actually quite a lot of flexibility in this course. You can imagine actually getting through this whole thing in probably as short as 3 hours if you're in a big hurry, or you could do full-time for 6 weeks. And so it really depends on how much interest you have in it. But my main objective is, like I said, is to get people through the experience, to see the whole thing, and then walk out and say, "Wow, I've got some experimental results." So for people who have never done silicon photonics, and in fact, actually myself, I really enjoy this component. Surprisingly, is a pretty fundamental one called the Mach-Zehnder interferometer, and it's a nice introductory one because it includes all the basic components like the waveguides, grading couplers, Y branches, and it allows you to start seeing some of the challenges in terms of the experiments. And so you don't get bogged down in months and months of layout only to find out that, hey, you drew your grading couplers wrong and your design is not testable. So it allows you to see, the testability challenges, the manufacturing challenges, and so on. And the part that I really enjoy is at the end when you get your experimental results back is to compare your experiments with your simulation. And so here's a graph that shows you this experiment and simulation. And you can see, for example, like little ripples or the free spectral range doesn't agree with what you thought it would be. And so this allows you to really do this comparison and extract parameters and then think about how to make a compact model for a waveguide based on this early experience. And then once you've gone through this process, then you can go on and tackle more complicated things. Now, of course, if you have more time, you can do much more complicated things. And so here's some example of some of the more advanced things. Bragg gratings are one of my favorite topics, and I talked about sub-wavelength structures as well. So that's on the bottom. Here's a directional coupler. You can make ring resonators with these sub-wavelength things, and they make excellent sensors. Of course, photonic crystals are a very popular topic. So here's one with a slot inside, again used for sensors, and then one-dimensional photonic crystals, slot waveguides, ring resonators, and then more grading structures. Okay, so that's kind of summarizes the workshops that we have available. So to recap, we have these 5-day intense 40-hour type workshops with a year-long design cycle. We have these very short courses at conferences that are about 3 hours with a fabrication, and then finally we have the online course which is 6 weeks and also has a fabrication. So next, I'd like to showcase a little bit some of the results from the SiEPIC community. And so these are people who have taken our workshops and then gone on to publish. And some people sent me slides, and so I thank those who contributed slides to this. And here's some examples from across the country. So we're going to talk about, I grouped this into a few different detectors based on germanium, ion implantation, and even single photon detectors. Then I'll talk about modulators for high-speed communications, then thermo-optic switches, discussion about polarization, some filters, lasers, and optical interconnect or optical input-output solutions. So first, here's a description of a detector. So these are using germanium detectors. This is fabricated through IME in Singapore. And what's different here is that this detector is actually a differential balance detector. So the idea is you have two inputs and one optical output indicated, or one electrical output indicated through this S signal. So this detector here includes the biasing capacitor and had a bandwidth of 16 gigahertz. And so you can see here some responsivity curves typical for these germanium detectors on the order of 0.7 amps per watt. Higher values have also been achieved through different designs. And what I liked about this work was that it was one of the early examples in Canada where people started packaging their devices to do more complicated things. And so you can see here some RF connectors. Here's the chip sitting on a ceramic package. And they were able to get 30 gigabit per second eye diagrams. And then they went on to do things that are much more complicated in the communication space, such as looking at, here's return to zero, DPSK communications, and comparing that to non-return to zero on-off keying. And then putting on some additional electronics at the output of the electrical signal. And so here's an example of looking at soft error detection versus hard error detection. So the idea is you have two thresholds for your eye diagram instead of one threshold. And what this allows you to do is you get an improvement in the data rate in reducing the errors. And so here you can see about a 0.8 dB improvement because you have essentially you're sampling more information than if you have a single detector, single sampling point. And then there's been more complicated things. So here you can see an example of going up to 50 gigabits per second. And finally, this is starting to be applied to coherent systems. And so here you see soft detection for coherent systems. And so you can see some of the components here. These are polarization split and grading couplers, hybrids, and a variety of these balanced photodetectors on a single chip. And again, very impressive. This chip was all packaged with the RF connectors. So that was work from McGill, from Odile Leboiron-Ladouceur's group. Next, we have from Andy Knight's group at McMaster. This is fabricated through IME in Singapore. You can see the cross-section of a waveguide. This is the red part is the waveguide, and then there's oxide in blue. And what's been done is this waveguide has actually been etched from the top, and so to access the waveguide. So I already mentioned this is useful for biosensor applications because you can put your blood and your chemicals on top of the waveguides. But it's also useful for ion implantation. So the oxide serves as a mask, and then you could implant defects into the silicon. And it turns out that the silicon actually becomes a pretty good absorber at quite a range of wavelengths. So I think the reason this paper made it into Nature Photonics is because this is a demonstration at 2 microns with very good results. All the previous work with ion implantation was done at sort of the 1.5 micron range. And the question is, can you make these detectors go to longer and longer wavelengths? And so now I think in this paper they go up to about 2.2 microns wavelength. And you can see the eye diagrams. They've achieved 20 gigabits per second eye diagrams with detectors and responsivity up to 0.3 amps per watt. And so 2 microns now could be this new window for communications because there's already fibers and optical amplifiers available. And now we have detectors, and modulators shouldn't be too difficult to design based on the PN junction. The next detector is perhaps even more challenging, and this is in the field of quantum information. And the idea is that you need to detect single photons, and this is done through superconducting materials. The way this works is you have a critically biased superconducting nanowire. So this is made of niobium titanium nitride, and this is biased, so there's a current flowing through the wire. But what happens is when you shine light on this structure, it actually creates an open circuit. And so if you bias this, then and hook up a resistor to it in parallel, you can actually get a switching event where it goes from high to a low. And it turns out that this is actually sensitive to single photons. And so the concept of this is Professor Jeff Young at UBC, who has been putting these in photonic crystals. And so you see a picture of a one-dimensional photonic crystal with this wire wrapped through the cavity. And so the idea is to enhance the field locally and so make the detector smaller. And here you can see the results of the structure. So this is fabricated through electron beam lithography. The wires are extremely small. They're 8 nanometers wide. These are the nickel titanium nitride films, and running at very cold temperatures. So this is 7 Kelvin. I apologize, 35 nanometer wide wire. And what's impressive about this is that the quantum efficiency of the detector is 96%. So you're really detecting single photons with the structure. And the reset time on this is very fast, so below 7 nanoseconds. And the dark rate, so we're talking about close to megahertz speeds of these things, and the dark rate is less than 0.1 hertz. And so you can see this is actually quite an enabling component for quantum information. And you can imagine having circuits with thousands of these detectors and eventually photon sources on a chip. And so, thinking about the future in our systems workshop, one day I imagine we'll be making quantum information systems through these types of structures. So more back to kind of the past and the present reality, PN junctions are kind of the heart of most of the modulator publications. And so here's a cross-section of the waveguide with your PN junction, and there's a phase shift associated with the voltage, and you can see if you put this in interferometer, you can see there's a shift to the spectrum. So a couple of examples of some of the modulators that came out of McGill. This is a Michelson interferometric modulator, where the idea is that you split the light into two paths, have a loop mirror at the end, and then the light comes back through. And so the light actually passes through the phase shifter twice, which means that this modulator is twice as efficient as if it was a conventional straight modulator. Now, you have to make this short enough to make it go fast, and so they did this with 500 microns, and they were able to get 40 gigabits per second with reasonable extinction ratios of 3.9 dB, and if you lower the bit rate, you can get higher extinction ratios. Another really beautiful modulator is one based on the traveling wave Mach-Zehnder interferometer. And so this is similar to the traveling wave modulators that many people are probably familiar with, except one of the challenges with those traveling wave modulators is how you connect the electrodes and the efficiency and so on. And so this modulator only uses a ground and a signal electrode for the microwave. So it's very easy to implement drivers for these or RF probes. And the way it's done is that the RF signal is actually split equally between the two branches of the interferometer in a push-pull configuration. So the junctions are kind of oppositely placed. Now, in order to do this, you have to bias the device. And so here you can actually see an inductor. Just this metal trace alone is enough to provide an inductance to bias the middle pin of the traveling wave modulator. And so here this is operating at close to 40 gigahertz. And eye diagrams have been measured up to 70 gigabits per second. So extremely fast modulation. And even more impressive, this is a post-deadline paper at OFC, and there's also a talk at the Optical Interconnects Conference, which showed, I believe it was 370 gigabits per second. And so now this is taking several of these modulators and putting them in a configuration where you have multiple bits on a single symbol. And so you can see at the very bottom of this chart, you have the symbol rate. So this is maybe, say, 40 gigabits per second, 50 gigabits per second. But we're combining multiple bits. And so you have dual phase. You have also multiple amplitude levels. And finally, you have polarization. And so all told, this allows you to get a multiplication factor of, in this case, 6. And so if your line rate is 56, then that gets you up to the 300-something, 340 gigabits per second aggregate rates. So next is an example, again, from McGill, from Dave Plant's group again. So this is a switching element. So this is a 4x4 optical switch, where the fundamental building block is a 2x2 switch, which is a Mach-Zehnder interferometer. And there's a phase applied to one or two of the arms. And this allows you to go, the pi phase shift gives you sort of left or right switching at the output. And these switches can be cascaded into very large matrices. One of the things that we found with working with these is if you're going to scale this up, power is really critical. And so we've developed, this is at UBC, we developed a phase shifter that's very efficient. So we've demonstrated a 50 microwatts per pi phase shift. And this is achieved using suspended waveguides provided by IME, and then careful optical design and engineering to try to recycle as much of the heat as possible to have as much impact on the phase. And so here you can see on-off ratios of 20 dB, and 50 microwatts is the total power consumption. So you can see it's almost a factor of 10 better than the state of the art, and about 1,000 times better than what is typically achieved if you don't etch the waveguides if they're simply on the substrate. So you can imagine if you have 1,000 of these, 1,000 of these switches would only use 50 milliwatts of power, whereas if you use the conventional one, we'd be using 50 watts of power, which would be way too much. Next, we can talk about polarization management. This is work from Joyce Poon, and so the idea is a lot of people have done taking the TE and the TM, or the S and P polarizations from the fiber, and you want to split them into two. And so if you're using the edge coupling approach, then you split it into TE and the TM polarizations. And then what we need is the components, which are the splitters and the rotators. And so this is the first foundry-compatible polarization rotator splitter. This was through OPSIS fabricated through IME, and this is available in our PDK library as a drag and drop component. And the way this device works is it takes your TE and TM polarization, which might come in from, say, an edge coupler, and it rotates. First, it converts actually the TM polarization into the TE1 polarization, and the TE1 eventually makes its way to the TE0 polarization. So what you're left with is two waveguides at the output, each containing the TE polarization mode. And the performance of this device is the polarization crosstalk is on the order of 13 dB. The insertion loss is less than 1.5 dB. And the device is several hundred microns long. Now, to improve upon this, Poon's group also added some filters essentially at the input. And so the idea is that you split the T and the TM using a directional coupler, and then try to strip away some of the parasitic T and the TM from the incorrect ones, and then use the polarization splitter rotator as a rotator to get back your two outputs. And so there you can see you can improve upon the crosstalk with the trade-off of a little bit more insertion loss. Now, what you can do with these is quite interesting. So you can, right now you can get from Thor Labs and Agilent and so on, you can get polarization controllers. But now imagine instead of spending thousands of dollars on one of these, you can actually build one on a chip for a few pennies. And you can have hundreds of these on a chip if you wanted. So this is a polarization controller example where you basically use phase shifters arranged in a Mach-Zehnder configuration. And the phase shifters are used to control the amplitudes and the phases between the T and the TM polarizations. And this allows you to get arbitrary polarization states. Now, this also works in reverse. And so if you have a random polarization coming from a single mode fiber, you can actually use this circuit to descramble and remove the anywhere from the Poincare sphere. You can get back to output in a well-defined TE polarization if you have appropriate control and tracking. So this should be quite a useful component for future systems. We also have some examples of optical filters. So these are optical filters using ring resonators, and this is work from Professor Jaeger, Shekhar, and myself at UBC, and looking at things like eye diagrams and power penalties and so on of what happens if you use single rings, multiple ring filters. Another work, this is Professor Wei Shi from Laval. So he works on contradirectional couplers. So these are essentially Bragg gratings except with two waveguides side by side that are different in size. And the way these work is you can use them as add-drop optical multiplexers, where you take an input and then you can split it off into a through port, add, and drop port. And what's beautiful about these is that you can actually design these to be single mode, and there's no other humps anywhere or bumps, unlike a ring resonator where you have a lot of peaks and a lot of effort has been gone to try to remove those peaks. Here you really have a single response, single passband, and it's very flat as well. And so this is very good for eye diagrams. You can see the minimal distortion in the eye diagram when you look at the data going through these contradirectional couplers. I apologize. The reference here is actually this is work from UBC from Professor Jaeger's group. The slide on the corrected, updated slides which I posted, I have the correct reference there. Another example. This is work at UBC as well. Integrating lasers with silicon photonics. And so the approach that we're taking is that we would like somebody else to do the fabrication. And so this would be taking chips from a foundry, silicon photonic chips from a foundry, and then VCSELs from a VCSEL manufacturer. So in this case, it's from Professor Aumann's group in Germany. So they provided the VCSELs. Oracle did the flip chip bonding, and then we show here the results of before and after bonding, the results of light coupled into a silicon photonic chip. So there's still some challenges with this approach. Polarization has been identified to be probably a big one. So quite likely we had the wrong polarization on the VCSEL, didn't match the grating coupler here. So there's quite a lot of loss in the structure, but potentially it's an interesting way of getting small amounts of power on a chip if you need them. The next discussion here is on how to couple to these chips. And so the chips that we get from IMEC and IME allow for surface grating couplers. And so most of our work is doing grating couplers, in particular the automated probe stations. And we also do edge coupling. So this is from PLC connections, an edge coupler connecting to a chip from IME. Now, Adil's group at McGill has been interested in high-density interconnects. So these are the profile from Chiral Photonics. And so you can see this is a 61-core fiber that has core spacing on the order of 30 to 50 microns, and these are all single-mode fibers. And so what's been done here is that this fiber has been polished, and grating couplers have been designed. So these are very small grating couplers designed to match the PROFA fiber. And they've done some communication experiments with essentially up to 61 of these. I don't think all 61 were tested in parallel, but the idea is to show that all 61 of these fibers work, and that in principle you can get very high density optical interconnects. And so if you remember, we talked about how do you get to terabits per second. So here's an example of a single optical fiber can carry 1.4 terabits per second. And the idea here is that a single silicon photonic chip can essentially provide this bandwidth and allow for very high density optical interconnects. So they've shown some of these. You can see the bit array diagrams, and that data actually does flow through these fibers. Okay, so let me get to some of these conclusions. So this is a conclusion that I kind of just take a step back and say, where is the field of silicon photonics today? Looking back 30 years ago, 40 years ago, the CMOS industry, vacuum tubes, and then the transition to 1 to 10 to 1,000 transistors. The transistors were not all that great at the time, but yet people were starting to make interesting systems. So it looks like that's kind of where we are as well. We still have lots of work to do in terms of coming up with PDKs and libraries, component libraries. And so a lot of the libraries that we have access through the foundries have individual components, but not very much in the way of parameterized. And so this is one of the efforts that we're trying to do, is emphasizing parameterized components, putting these in libraries, using the mature CMOS tools, and being able to support this kind of whole ecosystem where you can partition people into different roles. And so I already mentioned I'm not doing any more fabrication, so there's going to be some processing experts. There's also the people who make the EDA tools, so eventually I can disconnect myself from the modeling and I can just focus on the designs. And then there's going to be a group of people who are the component makers, and then those people make components, and they need to put those into a library. Of course, they need to make them parameterized, and they need to do lots of experiments to extract the parameters, and then put them into a PDK to share those with the rest of the community. Now, I should mention the incentive for academics for these PDKs is actually that we include a thesis or the journal paper as well as the layout in the library. And so the idea here is that for students, there's some inspiration that people will use your work, and that makes it more rewarding for you to contribute things. And so instead of just publishing a paper and having nobody use it, here you actually get to right away within a month of publication, somebody's already using your component and layout. And then, of course, we're going to have system designers, and so that's really the future of silicon photonics. Is 90% of the community eventually should be system designers. I mean, lots of companies, there's already 30 to 50 companies in the world making things in silicon photonics, and so this whole ecosystem will allow us to have accelerated product development and eventually increasing the size of the photonics industry, and then connecting us closer to the electronics industry. So in terms of the SiEPIC program, if you want to keep in touch with us, if you're interested in some of the research results or in the variety of educational and workshops, there's a LinkedIn page, there's a Facebook page, we have a mailing list as well, which we don't send too often. For the fabrication runs we do every 2 months, we have a Google group where we have a spreadsheet, and you can add your name to it if you want a chip, and we have the SiEPIC webpage. So thank you very much for joining me today, and I'd be happy to take some questions. And so you'll see on the Q&A page there's a way of typing in your questions, and I'll turn over the floor to the moderator.
Thank you, Lucas. As you mentioned, we're now opening it up to questions. Our first question for you, Lucas, is regarding the online course edX. Is it possible to get access to the fabrication after the course is over?
Yes, actually. So good question. A lot of people ask me kind of these things. How do I keep going once I do a workshop? And so the hook for that is that you can either purchase your own chip after you do your course if you want your own experiments, or because we do these runs every 2 months, it's actually quite easy for you to just keep submitting through the same mechanism layouts every 2 months, and then keep iterating on your design and make better and better designs. And so we have a lot of outside people who keep doing that. So absolutely, yes.
Okay. And our next question is the IME Activities Workshop open to people from outside of Canada?
Yes. So all the workshops are open to anybody. I mentioned that we didn't advertise much outside of Canada, but really we are open for business. And we've had a few people, as early as maybe 5 years ago who've taken our workshops. Of course, you have to get a visa to come to Canada. So if you're an international person, I think Canada is quite generous with travel visas. And the other part is, of course, the non-disclosure agreement. So you have to sign the agreements with the IME and the IMEC and so on foundries. And so that's the same requirement regardless.
Okay. And then we have a question about the e-beam fabrication is $1,200 for academics. How about for individuals and or companies?
Yeah, good question. So what's the cost for e-beam fabrication? So for that, I would have to direct you to Rick Boyko. So the cost that I get as an academic and the universities get is because there's some university sponsorship involved in this. And the academic rates, I know that their e-beam costs posted on their webpage are about 2 times more per hour. And so I would imagine it would translate roughly to a factor of 2 in cost. So you can contact Rick Boyko through. If you can, feel free to email me if you want the information. But he has a web page and you can ask him for it. And so like I said, it's about a factor of 2. And I know there's quite a few companies who are taking advantage of Rick's time, and it's kind of putting a burden on him in terms of slowing down my fabrication runs because he has so many customers. But I know that they're expanding and hiring people as well. And so I guess if you know anybody who's looking for a job, I think Rick's looking for people.
Great. Okay, our next question is, would a 2 micrometer optical interconnect be possible based on silicon photonics technology in the near future? Yeah, so the 2 micron interconnect. So the detector was probably one of the hardest components to address because germanium has the absorption ends at about 1.56 microns. And so what that meant was that links could only really be done to up to 1.5 or so microns. So the fact that we now have a detector that works up to 2 microns and beyond is really the key enabling technology. And they were able to show these eye diagrams and so on. So it means that there's a laser involved, there's modulators that were done, and the detector as well. So I think all the key pieces are there. Now, if you're talking about short reach interconnects, you don't need the optical amplifier, but if you want to go longer distances, you'll need the amplifier. So I think absolutely 2 microns interconnects are possible. The question is, is that a new standard that's worth adopting? Maybe once we exhaust the bandwidth of the 1.3 and the 1.5, then that would become could be the next band. Okay. Our next question is it possible to get a smaller bandwidth in the contradirectional couplers?
Yeah, the bandwidth in the contradirectional couplers, this is actually similar to Bragg gratings, where it's the index of refraction contrast of the grating that determines the bandwidth. And so what I like about these Bragg grating and the contradirectional couplers is you can go all the way from, say, maybe half a nanometer bandwidth all the way up to, I think the largest we've done is a 30 nanometer bandwidth. So this can be used for both coarse WDM or dense WDM communication filters.
Okay. And we have another question, which is, are there any specifications for the fabrication, such as material, thickness, minimum motif size, etc.?
So fabrications for fabrication. So I guess I wish I could ask you, whoever's asking it, this is Samuel, if which specific foundry you're thinking about. I'll give you all the answers. Hopefully that'll briefly cover it. But for the foundries, if you're going through the foundries, they're typically using 193 nanometer lithography in the case of IMEC. And recently, IME is also switching to that. And so the minimum feature size that we've been able to get is slot sizes in a slot waveguide of on the order of 120, 130. It might not be very reliable there, so you might want to go maybe a little bit more like 150 nanometers. So that's the minimum feature size there. And in e-beam lithography, we've done like lines and holes as small as about 60 nanometers, but that's right on the edge of the photoresist or the electron resist and so on process. So 80 is a bit more reasonable. And in terms of thicknesses, we've gone with a standard, what everybody else is doing in the world, which is 220 nanometers. We've done some work in other thicknesses as well, but we kind of are happy to support the standard. It's not the ideal standard. So, for example, Luxtera has chosen 300 and something nanometers for their process, and that's specifically optimized for the grating couplers. But we've gone with what the MPWs are doing. So why 220 nanometers is standard? I guess I just saw Min ask the question, so thanks for the related question. 220 was actually, I spoke with Wim Bogaerts. He actually he told me he just kind of picked it out of the air, really. I mean, he did some simulations of the slab waveguide, and you can see that it's actually the single mode condition where below, I forget what the exact number is, but 220 turns out to be single mode in the TE polarization. and so it was chosen essentially to be single mode waveguide. But since then, we found that it's possible to make, sort of, you can excite single modes in different types of thicker waveguides and thinner waveguides. So really the answer 220, it turns out it was actually one individual who picked this standard for his PhD roughly 15 years ago, and it's kind of stuck because all the multi-project wafer services started offering it. So.
All right. Our next question is, what happens to IP or intellectual property if something new comes out of the workshop?
Yeah, okay, so intellectual property. So it depends on which workshop. So in general, we do not take any ownership of anything you do, and so we've had people go and patent things after the workshops, and of course people publish things. People have started companies coming from our workshops, and so you own everything. What we've done is we've done our effort to create a community where people trust each other and don't disclose anything when they're not supposed to. And this is actually helped by the fact that we have non-disclosure agreements. And so, in particular, in the active and the passive workshops through IMEC and IME, all the participants in the universities have to sign a non-disclosure agreement, and it means that anything that you submit is and is merged onto the multi-project wafer chip is actually confidential, and that people who are looking at the chip cannot share that. And so we've never had any incidents of breach of IP since, I guess, 2008. So hopefully, I think this model is sort of both a trust and an NDA model that works pretty well. Now, the edX workshop is a little bit different. We don't have any NDAs or nothing. It's really just you just pay and come. And so for that one, that's a bit more up in the air. I can say that if you really want to take the online course and you have something confidential and you don't want the rest of the class to see it, I can merge your layout separately and then put it into the chip separately, not share that. This would be a little bit more effort, but we've done that for people before. And so let me know, Amir, if this is of interest to you.
Okay, and with that answer, we'll be wrapping up today's webinar. I would like to thank you, Lucas, for presenting today, and say thanks to the NANO Photonics Technical Group for organizing this webinar, and thank you to everyone for attending. This concludes today's presentation.
Okay, can I just jump in? Maybe there's a couple of extra questions, so maybe what I'll do is I'll answer those questions. So Abdul, I'll answer your question on the LinkedIn page. So feel free to add more questions on the LinkedIn page where I posted the slides, and if there's anybody else who has more questions, more details, we can add more links, and I can get you in touch with answers.
Thank you very
much, everyone.
Thank you so much for doing that, Lucas. We appreciate it. And that concludes today's webinar. Thank you, everyone.
Bye-bye.